And first, I wanted to talk a little bit about the framework where my project is situated. It is a part of a large research consortium, which is nationwide in Switzerland, called NCCR Evolving Language. It involves 30 research groups from multiple institutions across Switzerland, with the main hubs being University of Zurich and University of Geneva. It's an interdisciplinary endeavor to uncover everything that we can possibly know about language and understand its origins and predict its future. And so my project and what we're doing here at the University of Zurich and my team is we're sort of responsible to try to predict what's going to happen with our language in the future. Specifically my PhD project, the research question is, what impact does automatic language generation have on linguistic intuition and language evolution, with a somewhat semi-clever acronym IMAGINE? And it's a very large question and hard to answer, and there is no research paradigm really that is established already to research something like this. But breaking it down into smaller sub-projects, I have two directions. One is a corpus linguistic direction, where I look at how machine-translated and AI-generated texts differ from human writing, and this is what mostly I'm going to be talking about today. And the other sub-project is psycholinguistics, where I already go directly into measuring the impact that machine translation might have on linguistic production of language learners. And in the very beginning, somebody asked me, why bother with machine translation if you don't ever use it? Many people don't use it. Why would it even have an impact? Which is an interesting thing to say, because even if you don't use machine translation, you most probably are surrounded by it and you're exposed to it without even realizing that. And indeed, just looking at Google Translate alone as a system, it had about 1 billion installs in 2021, and the number of uses of this one system is only growing. And there are other systems that are also incorporated, for example, in like Google Translate here is hard-coded into one city's website, and that's just one example that came out a couple of years ago. Or the Swiss government administration acquired DeepL license also several years ago, and there might be documents that are produced that were translated by a machine. Or as one other example is the academic publisher, Springer Nature, also acquired DeepL license to provide free translation to researchers whose native language is not English. So these are all good endeavors and they're good motions, but this is just very little example of where we might see translated text without necessarily being indicated that it's been translated. And now, of course, with large language models and things are maybe getting out of control, so to say. For example, in March 2021, that's even before ChatGPT, it was estimated that GPT-3, the largest model available at the time, produced about 80,000 books worth of writing a day, which amounts to an entire US public library. That is an interesting amount of generated text being produced. And after ChatGPT came out, so in February 2023, there was already some research pointing out that ChatGPT produces the volume equal to all the printed works of humanity about every 2 weeks. And this report was cited by the National Bureau of Economic Research in the United States. So the amount of generated text that's around us is quite substantial, and it is only logical and quite natural to ask ourselves if all of that might change the way we use language. But how long have we been exposed? And I actually would like to ask you whether you have an idea of when this happened, or this sort of cutoff year, that before that we were not exposed to machine-produced language, and then after that we can say, yes, starting now, everything that we produce might have been affected by generated language. Just think about that. But in the meantime, I would like to look a little bit into the history of the development of language technology. And this is, okay, this might not directly be related to my talk today, but I just learned this story recently, and I was inspired, and I thought that I would like to tell this story to you, especially now that there are so many scandals surrounding AI and specifically language technology. I found it fascinating and somewhat comforting to remember that all of this started with inspiration and the vision and determination. So Father Buza is considered to be the pioneer of computing in humanities. And he was an Italian Jesuit priest who, during his PhD, was working on the metaphysics of presence in St. Thomas Aquinas' works. And he was investigating this presence, meaning the physical presence of Jesus, through analyzing function words. And he created Thomistic concordance with 10,000 handwritten index cards. And then he was planning to expand that and create even a bigger version with 13 million cards, but realized that it's impossible to do for a human. So he wanted to speed up the process and looking for automated ways of maybe doing that. So he traveled to New York and met with Thomas Watson, the founder of IBM, and convinced him to use computers to start processing language. And at the time, it was considered to be impossible. But yet he managed to convince Watson, and in 1951, they produced the first machine-generated concordance, and that was even before the invention of programming. So a couple of decades later, machine translation system already went into space. So Systran, one of the oldest machine translation companies, provided its product for the Apollo-Soyuz project, for example, and for the European Commission in the mid-70s, and also was built into Google's language tool. And those were rule-based systems that can be quite good, but every rule has to be written, has to be created, and it requires a lot of linguistic expertise and collecting quite an extensive vocabulary, because if the rule hasn't been written in or the word hasn't been put in, the machine translation will fail. And also it was, for example, very hard to incorporate semantics into a system like that. So for languages that have a different word order, there could be very clumsy translations. So machine translation might have gone to space then, but on Earth, humanity, I would say, was not really exposed to generated language at that point. But then researchers discovered that computer programs can learn to translate text by analyzing large volumes of already existing human translations and by identifying language patterns within them. And these computational models, they calculate probabilities based on pairs of existing translations. And when faced with multiple translation options, the system selects the most likely one, the most probable one. So these are called statistical machine translation systems, and they can even translate sentences that they have never encountered before by piecing together known words and known phrases. Of course, if the system has never seen a word or a phrase before, then that can create a problem. But these statistical machine translation systems were used, for example, by Google Translate for a decade between 2006 and 2016. And at that time, already the concerns about our exposure to machine-produced text kind of started growing a little bit, even though I don't know if you remember or used Google Translate back in those days. But here I found an interview published by Zeit Online in 2014, an interview with Anthony Pym, the president, who was the president of the European Organization of Translation Studies at the time. And his words are, machine translation often still sounds clumsy, but before that is perfected, people's tolerance for this clumsiness is more likely to increase. Machine translation will change the established languages, just as more and more Anglicisms have crept into German in recent years. Well, but then, of course, neural networks came into the picture, and the world was never the same. Google Translate adopted this technology in 2017, and now all machine translation systems and large language models use this technology. Neural networks also use probabilities to predict the next word, but they churn through data in a much more complicated mathematical way. For example, you can take a look at this toy neural network. It has a number of nodes, which are nonlinear functions, also weights and biases that connect the nodes. And if we count all of them together, we can sort of get the number of parameters for this system. So this toy example has, let's say, 64 parameters. But how many do real neural networks have? Well, in 2018, Microsoft claimed to have reached human parity with their Chinese English machine translation system. The claim was, let's say, maybe a bit premature, and then was confronted by other researchers. But the neural network that was powering this machine translation system had already millions of parameters. And this is just an interesting fact for you, that modern large language models like ChatGPT, they're in order of magnitude larger than the first neural systems. For example, ChatGPT is estimated to be about 1.5 billion parameters, and GPT-4 is 1.76 trillion parameters. So that's even hard to imagine. But I would say I consider 2017 to be that milestone, the milestone that started our subtle exposure to generated text at scale. Well, as machine translation became much better, meaning rather fluent, but now there were other concerns. In 2021, for example, Van Mansenhove et al., they started investigating whether algorithmic biases in machine translation can lead to an artificially impoverished language. And they worked with English, French, and English, Spanish translations and investigated statistical systems and neural machine translation systems. And they used several metrics to measure lexical and morphological diversity in the training data and in the output. And they established that there is definitely a discrepancy between the two. So the data that goes into machine translation system is much richer lexically and morphologically than what comes out. And if you, as they argued, that if you keep feeding that data back into these systems, then language becomes less and less diverse. And they call this machine translationese. So we followed that line of research, but decided that rather than training our own systems like Van Mansenhove et al., we investigate the output of commercial machine translation systems, because for my PhD, my research, it's more important to look at a larger, broader impact that these systems have on humans in general. So we looked at several systems, and you can see them color-coded here on the left. Looked at Microsoft Azure, also known as Bing, DeepL, and Google Translate, and at one local Swiss machine translation company, which we anonymized for the submitted paper, and here it's called MTX. And we analyzed seven different corpora of different domains, and here you see the results for just one corpus, namely one novel, Jane Eyre novel from the Gutenberg project. So this spider graph in the middle represents the corpus, and the spokes on the spider graph, they signify different metrics. So specifically 8 different metrics that are listed on the right. The colored areas within the graph, they show how well or how the values that each system scored for each metric. So if we look, for example, at lexical diversity, which here is represented as type token ratio, Yule's index, and the measure of textual lexical diversity, we can see that different systems score differently. And also they differ from the human results, which are marked by blue. So the blue line inside, this is human translation. And we can observe here that, just speaking of diversity by itself, that some systems, and namely here it's the MTX, our anonymized company, and DeepL, or here it's Google, actually, they exhibit higher diversity, higher lexical diversity than even the human text. Then we can look at sophistication that has 3 different frequency bands. So band 1 shows the proportion of text that is occupied by 1,000 most frequent words. So this is the words that repeat all the time and how much of the text they populate. Band 2 is same, the proportion of text that occupied by 1,000 to 2,000 most frequent words, and band 3 is already the least frequent words in the text. And again, on the spider graph, you can see that, for example, MTX converges with human results, but on the band 3, it shows much higher diversity, for example, even than other systems, and even than the human texts. And finally, looking at the morphological richness and its metrics, here we use Shannon entropy and Simpson diversity. Different metrics, but they measure the same thing. They calculate the level of surprisal within a particular lemma's inflectional paradigm, which is relevant to morphologically rich languages like German. And here, yes, I forgot to mention that we use a different language pair. We look at English to German translations. So here we can see that also some systems, namely DeepL, exhibits rather rich morphological diversity. So here we can assume that, considering that machine translation keeps improving, and there are also systems that work better for certain languages. In our case, DeepL is known to work really well for German, and our local machine translation company is also customized to process German. So setting the issue of quality of translation and the appropriateness of translation aside, machine translation can probably not be held responsible for general lexical impoverishment of language. But of course, more fine-grained and qualitative analysis would be appropriate. We also assessed the extent to which machine translation models participate in the anglicization of German. Here you see the results for 2 corpora from the same study, where the number of anglicisms and human translation is taken as 100%. And here on these bar charts, they represented as blue bars. And the use of anglicisms varies across systems and even across humans. So for example, on the right in the WMT21 corpus, we have 3 human references. So here they're indicated as human A, C, and D. And we can see that they use different number of anglicisms in their translations. But there was a general trend that we observed that some systems tend to use more Anglicisms and some systems tend to use fewer Anglicisms. So for example, Microsoft Azure tends to use more Anglicisms than humans in their translations. And you can see it in the example sentence here. Whereas DeepL tends to use fewer Anglicisms and prefers classical German translations. Like here it uses Fahrrad, for example. So we could, based on this study, we could make assumptions maybe that machine translation might play a role in the Anglicization of German or de-Anglicization of German, depending on the system, because there are still some slight differences. Then we also looked at syntax. And here, I don't know how many of you speak Russian, although it's not necessary for this exercise, but just looking at the word alignments alone, I wonder if you can guess which translation pair belongs to a human translator and which was translated by a machine. Maybe to make it easier for you, here's a English to German translations, also with word alignments. And as you can see, some word alignments maybe are not the best. This was an automatic word alignment system that did that. But so maybe it had a difficulty finding the right alignment in certain translations. And if you guessed this, then you're correct. And the interesting thing is that we can tell the more complicated the alignments are, the more confused the system is in aligning the words, then it probably is a signal that maybe this is a human translation. And it was shown by previous research that syntactically, machine translation systems, they tend to follow the structure of the source sentence. So we, again, measured that in all of our corpora, and we used the measure of syntactic equivalence, which looks at the total number of word alignments in a sentence, and also combines it with the number of cross alignments between the source and the target and the translation, and produces this metric that shows maybe how creative or how diverse syntactically the translation is. So here the higher score indicates more syntactically creative translation. And as you can see, it is quite, it looks the same across the board. For all corpora, the result is the same, that human translation is quite syntactically diverse and all other systems score much less. And there is a maybe bigger concern that comes up with these findings, because considering that many translators are becoming post editors now, there was a psycholinguistic study done in 2017 that showed that even during post editing, alternative translations become inaccessible. So once a translator already sees the output of machine translation, it is hard to change the syntactic structure of a translation. And considering that there is this syntactic simplification that might be happening by machines and then affecting humans during the process of translation or post-editing, there might be more serious impact on language and needs to be investigated further. So, but what about ChatGPT? What is the linguistic profile of ChatGPT? It was reported before that ChatGPT writes as a conservative team of experts. Its writing has been described as informative and objective, well-organized and coherent, formal and academic, writing with an argumentative style, which lexically shows itself through a higher number of nouns, adpositions, and conjunctions. It's also been observed that it produces texts that have a poorer vocabulary than human texts. And sometimes it uses fancy words or words that are atypical for a particular domain. But unlike machine translation systems, language models, and particularly those which were trained to answer questions and hold a dialogue, like ChatGPT, for example, these models are rather diverse, and the output also heavily depends on the questions or the instructions that we give to the model. So some research showed that prompt alterations, because this is how we talk to these models, prompt alterations affect the output. So that lexical diversity depends on in this particular study, they were investigating formal and informal texts. So lexical diversity, for example, is much higher in formal texts. So it depends on the formality level. And also part of speech distribution changes depending on how we prompt the model. And this, since these commercial models, they are updated continuously, at some point it became possible to choose a system setting called persona. And this is a parameter that we can sort of instruct the model to write as a particular person, as a particular type of person. And it helps shape the output in terms of information and style. So here there was an interesting study, and all of these studies are done in this year because the field moves quickly. And but here they took a list of about 70 different personas, politicians, journalists, famous people, and also made-up people, not necessarily historical persons. And these researchers noticed that the language that the system, that ChatGPT produces based on the persona changes drastically. And here specifically, they were measuring the level of toxicity. And it is known that these models, they're heavily moderated to make sure that they don't produce toxic or offensive language. But yet this could be overcome by just asking ChatGPT to be a particular person. And depending on the person, the level of toxicity was lower or higher. So for example, Coco Chanel talks in not a very toxic language, whereas Adolf Hitler produced the most toxic output. Oh, thank you. Thank you, Martina. I will take a look at it later. Okay, so we decided to go deeper into this question and look at the linguistic profiles of ChatGPT personas. Because all these descriptions that I provided before were about generic prompting of ChatGPT, because even in the beginning of this year, we were still copy pasting our texts into the browser, and then all these other features appeared later. So here in this latest research, we decided to analyze linguistically what different personas can produce, rather than working with some specific historical or real people, like in the previous study. We looked at more synthetic combined personas that are based on the tasks that maybe are given to ChatGPT most often. So, for example, one of the most trivial tasks is to continue writing text. So this was our completer persona, where we just ask the model to continue, or to explain text. So that was our explainer persona, and also to create a new content, and that would be our creator persona. We looked at journalistic and medical and academic texts, and we broke them up into a title, first paragraph, and the main text. And depending on the persona, we provided different parts of this text to the model. So for example, for the continue or for the completer persona, we put the title in the first paragraph, provided that to the model and asked it to continue creating the main text. For the explainer persona, we only provided the main chunk of text and asked the model to explain it. And then we used the main chunk of text written by humans for reference. And we did it for English and German texts. And here on the left, you see the example of the creator persona for the journalistic domain and specifically the English corpus of CNN articles. So here we instruct the model. You are a journalist writing for CNN, which has a high reputation for its journalistic coverage of a wide range of news topics, including politics, world events, business, technology, entertainment, and more. And then the prompt itself goes like this. Use this truncated CNN article as an example, and then we provide the snippet. So this is for the creator persona. It means we provide the title and the first paragraph. Imagine a different newsworthy event that happened in the location mentioned in the article. Write a full news article about this imaginary event, matching the writing style of the example text. Write about 600 words. So we created these these comparable corpora for each persona, and then we analyzed them in terms of linguistic features. And now I'm going to show you a lot of these box plots. So let's spend some time on this. Here, the green box indicates the human texts, human writing, whereas the completer or continue texts are marked by the yellow boxes. The explainer is in purple and the creator is in red. And so here we look at unique tokens because that was one of the features that was most prominent, at least in the previous research and in my own preliminary studies when I was still copy-pasting texts into the browser. It seemed like the proportion of unique tokens in a text could separate human writing and generated texts apart in the most obvious way. And here on the left, we see two examples from two different corpora for German, and all of these are for journalistic writing right now. And we can see that this trend holds, that German human texts exhibit the highest proportion of unique tokens, whereas generated texts already sink. And especially the explainer seems to be the least lexically diverse. And the creator is trying to match the human texts in terms of the proportion of unique tokens. Yet on the right, you see English corpora also for the same domain, for the journalistic domain. And it seems like here it's already different, that in fact, human texts seem to have the smallest proportion of unique tokens, and the creator persona just is the most linguistically diverse, although this was more of a distant reading exercise. So I only looked into the actual produced texts only marginally to make sure that it is not total gibberish, but there might be some hallucinations or might be some other problems, or maybe it is really took its creative task to heart and created a very linguistically, lexically diverse text. Then we looked at a part of speech distributions, and here the trend seems to be exactly as predicted and as shown by previous research. So for example, for nouns, we can see that all the texts from all personas exhibit a higher proportion of nouns in texts. And the same goes for verbs, for both languages, for English and for German, across all domains. And that seems to be quite a distinctive feature for to tell the human texts apart from generated texts. And the same for adjectives. Another interesting feature that we took a look at was readability. And here we used 5 different readability metrics that worked better for English texts rather than German texts. So here you see the results for the English corpora, for the combined English corpora. They all seem to indicate the same thing, is that generated texts are harder to read than human texts. And so we used Gunning Fog and LICS and Automated Readability Index, Flash Kincaid Grade, and Flash Reading Ease. They take into account the length of sentences, the length of words, the number of complicated words, which usually is like longer than 6 characters. So things like that. And it seems like generated texts are, at least based on this automated readability metrics, are harder to read than humans. Also coherence, even though it was shown before that generated texts are less coherent than human-produced texts, but automated coherence metrics kind of show a different picture for both languages. This is also combined results for all English data and for all German data. Now we measured first-order coherence, which looks at 2 adjacent sentences and measures a cosine similarity between them, and also second-order coherence that looks at 2 sentences apart. And it seems like the results are the same, that generated texts are more coherent, whatever that means. Probably because humans still, I think that in generated text, the models might still repeat certain words from text to text, from sentence to sentence, whereas humans can actually move on with writing without necessarily repeating the same word that was used in the previous sentence. And the most distinct features are the simplest ones. Maybe it's kind of surprising, but maybe understandable. One is a sentence length, and specifically the standard deviation, which indicates how much sentence length changes in a text. So this is also for combined data altogether, English and German. So maybe that's why the bars don't seem to be, or the boxes don't seem to be as far apart, but the statistical significance test showed that this is definitely a significant feature. But so human sentences, they tend to vary in their length much more than generated sentences that are mostly produce sentences of more or less the same length. And the proportion of punctuation. This was also indicated by previous research that humans are much more creative with punctuation, whereas it's quite standardized in generated texts. And humans use punctuation to express emotion, and generative models, they are conservative teams of experts. They don't express any emotion. And so the punctuation is usually quite standard. So to conclude, well, I would say we are surrounded by generated text, and it is fluent now and of high quality, so it's hard to detect, but there might be some biases that can affect our language, and so it should be studied, and ongoing research should continue, because the models, they keep improving, they keep changing, and the best models right now are commercial and they're not open source. so new features appear and we have no power of or no control over it. And lexical diversity might not be the main problem, or the loss of lexical diversity might not be coming solely from generated text, but the appropriateness of vocabulary that is used by the models and that is used in machine translation, and also the style of writing that needs to be monitored and probably studied further. And syntactic impoverishment is an interesting topic because at least with neural machine translation, the trend seems to hold that the translation systems, they mirror the source syntax and the sentences become more and more standardized. With large language models, there is no research as of yet about that, but and so that needs to be investigated basically, and whether where the impact on our language can come maybe from the syntactic side more. But this is it for my talk for today. Thank you for your attention, and yeah, I hope you liked